I don't know if you all appreciate it, but we're just past about in July. The James Webb Space Telescope has been in operation, science operations, for 2 years. When I was looking to find a speaker for tonight's meeting, I reached out to the JWST operations team and said, "Hey, could you give me a reference?" And I got an email back the same day that I asked the question, and the lady who runs the media group there for JWST said, "You really should get a hold of Dr. Morley from University of Texas at Austin. She gave a great presentation, and I highly recommend her." So I reached out to Dr. Morley, and she has kindly agreed to tell us about her research using JWST for exoplanet studies. Dr. Morley is an associate professor at UT Austin, and she studies the atmospheres of exoplanets of all types, all shapes and sizes, and simulates those atmospheres using theoretical models in order to measure properties of atmospheres from afar. This includes the atmospheres of terrestrial planets, super-Earths, gas giants, brown dwarfs, and everything in between. Dr. Morley received her bachelor's degree in physics and in Earth atmosphere and planetary science from MIT, and her PhD from UC Santa Cruz before joining Austin in 2018, UT Austin in 2018. Dr. Morley was also a NASA Sagan postdoc fellow at Harvard University. So please welcome Dr. Carolyn Morley.
Great, thanks for that introduction. I will go ahead and share my screen. There we go. And okay, it's great to be here. Great to talk to all of you. I'm currently teaching an intro astronomy class, and I've been making them go and do some like amateur stargazing for the last couple weeks in the night sky. So I actually had to look up like the fact that Saturn is up right now for them to look at. So I always need expertise of people who actually look at the actual night sky here. It's been cloudy for the whole 2 weeks that I've assigned this to them. So I had to give them an extension just so that the skies would clear up. It looks good today, though, so we're back in business. I'm excited to tell you today about exoplanet atmospheres. So I've been studying exoplanet atmospheres for the whole time I've been an astronomer, but really the last 2 years have been the most exciting time to do this because we have this new shiny telescope, the James Webb Space Telescope. So I'm hoping that I convey some of our excitement about that facility and show you some of the early results as we learn to use this observatory and start seeing things that we've never seen before. So we'll go ahead and jump in with a little bit of context of exoplanets, what we're looking at in the night sky. So this is going to be a movie. So this is a picture of our galaxy. And as the movie plays, you'll see planets pop up on the screen as we discover them. So we start in the early 90s when we first started discovering exoplanets, and we'll march through to 2022. So I'll go ahead and play it. So at first, this happens slowly, right? That we just find a few planets every year in the 1990s. We start finding more and more planets. These are mostly found with indirect methods of finding planets in the first year. So we're looking at the wobble of the star as the planet tugs on the star. And then we start actually designing some missions and then launching them around 2008 that are custom designed for looking at planets as they actually cross in front of their host star. We call this transiting planets when they cross in front. And you'll start to see a bunch of planets that start to appear right in one section of the sky over there. That's the Kepler field from the Kepler Space Telescope, which was custom designed for this. And you start to see more planets all over the place as we get better and better at finding them and have more kind of custom missions for finding them. 2022, we hit 5,000 known exoplanets outside of our solar system, which is a really fun milestone to pass through, right? Seems like a lot. So we just see these planets all over the sky through these methods. So the bottom line now is when you look up to a star, like any star that you see in the night sky, that star likely has a planet orbiting. But one of the cool things we've learned by doing this, right, is that that planet may look very different, actually likely looks very different than the planets in our own solar system. And so let's look at that on a plot that astronomy people like to show a lot. So we're going to populate this with planets, but let's look at it first. So this is period on the x-axis, so the length of time the planet takes to go around its star, then the mass of the planet on the y-axis. So we'll populate the planets from our own solar system first. This is where they plot. Jupiter, Saturn, Uranus, Neptune, right, our giant planets on long orbits. Earth and Venus, Mars, and then Mercury and Pluto just like fall off the bottom of this plot. They're too small. And so now we'll put the exoplanets up here and see how similar they look to the planets in our own solar system. And they fill in the plot, right? We see planets in all kinds of orbits, planets with all kinds of masses from very small planets up to very big planets. And we see planets, actually, some of the very first planets we discovered were the planets over here, right? These Jupiter-sized planets, right? They have the mass of Jupiter, but they're in orbits that are like 1 to 10 days around their host stars. So these are hot Jupiters, hot because they're close to their host stars. They're just whipping around their stars, right? There's nothing within right, the orbit of Mercury in our own solar system, right? An 88-day orbit around its host star. So this was really surprising. People didn't even believe that these were real when they were first found, but they are. They're really there, and we can study them in detail now. And so what I do, and a lot of my friends do in this field, is actually take these planets and try to see what the atmospheres of these planets are actually like. And so we take advantage for many of these by looking at these transiting planets, these special planets that just happen to be aligned. So they cross in front of their host star. They also cross behind the host star when they kind of go around the other side. So during the planet's transit, right, when the planet is in front of the starlight from the star has to go through the planet's atmosphere to reach us. And so the planetary atmosphere itself imprints on the light from the star. Likewise, when the planet goes behind the star, right, the star actually blocks all of the planet's light. And so if you look at a planet like a hot Jupiter over its whole orbit, you might see something like this. So this is over the whole orbit of the planet. You see that the planet, when the planet crosses in front of the star, we lose a lot of light, right? Kind of a percent or two of light from the host star, just because we blocked some of the light out. And then we start seeing this light go up a little bit here, right? This is plotting light from the star over time. So you see the light go up here. That's as the day side of the planet comes into view. The day side is hot. And then you see this little dip. This is just the planet disappearing behind the star. And you get this little tiny dip in light. We can do this not just at like one wavelength, but we can break the light into a spectrum and do this exact same technique for both transit and eclipse, split up the light and get a spectrum of our planet. So that might look something like this. So now we've taken this light from during the transit and broken it up into colors. These are infrared colors from about 1 to 1.6 microns. And we can do the same thing for our eclipse here. So we're measuring the eclipse depth, right, as a function of wavelength to put together then something that looks like a spectrum, right? So this one on the top, this is the eclipse depths from this plot, plotted as a function of wavelength. And we can do the same thing here for the transit depth. And we see this little tiny change in the transit depth in both, right? In both this emission up here during the eclipses and in here during the transits. And we know, I know, because I've looked at these plots a lot, that this here, this dip in the middle, that is a water vapor feature. And so what we're detecting here is water vapor in this giant planet atmosphere. We expected to see that, so that's good. And we can then, do things like getting a constraint on how much water vapor is in the atmosphere. Is it what we expected? And so we can do this not just for this wavelength range, but lots of different wavelength ranges where we can see different molecules. And this is kind of the state of the art of what we could do pre-James Webb. So circa kind of 2015 to 2020, this is the best we could get. And this is actually stitching together like lots of observations that were all taken in small chunks to do this. So I look at this and I see a few things right away. I see these high points up here. This is actually sodium, like atomic sodium in this planet's atmosphere. We also have sodium in our own Earth's atmosphere, and potassium down here. So that's what's causing these points to be higher, right, of a deeper transit than any of the rest of these. I also see this really characteristic, right, kind of bump, bump, bump here. All of those are water vapor features. We see these 2 points out here. This is kind of the best we could do out at these thermal infrared wavelengths, kind of 3 to 5 microns before JWST. You'll see this change in a minute. We just had 2 points. You can see this one's higher, and we said, okay, well, CO2 absorbs there. Maybe we're seeing CO2 there, but it's hard to tell from just 2 points out here is not a strong constraint. And then we see kind of a slope here, and we think that's from clouds and hazes in the atmosphere. Okay, so that's the best we could do circa 2020. Enter James Webb Space Telescope. So it launched on Christmas Day in 2021. It's like the best Christmas present that astronomers have ever gotten and ever will get, I think. And it's a 6.5-meter telescope. It's different from Hubble in that instead of looking at short wavelengths, right, visible wavelengths in the very near infrared, it's looking in the infrared. And it has really high sensitivity. We're able to see really, really faint things with JWST. And it has this really broad wavelength coverage where we're actually able to go from about 0.6 microns all the way out to 28 microns. And so that's fantastic because we can see lots of different features in exoplanet atmospheres when we have that broad wavelength coverage. So with just a single observation with each of these 2 instruments that are both kind of near infrared instruments on JWST, this is some of the very first observations that we got. This one on the bottom is actually the very first observation that I saw, like looking over somebody's shoulder at a conference, and they were like doing the data analysis in real time just after the data had been released to us as astronomers for the very first time. He like presses go and it pops up and we all gasped, like literally like this room of astronomers, like our jaws dropped. We were like, this is amazing. This is going to be amazing. This is like launching the next 10 years of science that we're doing. So why were we excited? So this is that region where we just had those 2 points before, right? We had like a 3 micron point and a 4 micron point. We're like, maybe that's CO2. And now you can see this bump here where we have like dozens of data points. That is that CO2 feature that we thought might be there, and indeed it is. And so we saw some things that we expected from our prior observations, but then we also saw things that we didn't expect. So this feature here, the sulfur dioxide, little bump in there, that's not a feature that we modelers predicted would be there. It turns out that it's from the interaction with the starlight from that host star. So the starlight for this planet, which is like a hot Saturn mass planet, is actually breaking up sulfur at the top of the atmosphere. That sulfur is interacting and it's making SO2, which wouldn't otherwise be there. So that's cool. We learned something kind of brand new as well. So this is the kind of thing we can now do for our kind of hot Jupiters, hot Saturns, hot Neptune mass objects. But I wanted to tell you something that I think has been really exciting that my group has been really involved in, where we're actually trying to look at planets that are more similar to the planets in our own solar system. And so we're going to think first about the giant planets. And so let's look at Jupiter. So Jupiter is cold, right? Jupiter is about 130 Kelvin. But JWST is really sensitive. And so it's sensitive in the infrared where cold things are bright. And so we actually have a chance at looking at kind of Jupiter analogs outside the solar system. And we have a really fantastic place to start, which is a group of objects that I will variably call free-floating planets or Y dwarfs. One of these sounds more exciting than the other. We usually call them Y dwarfs. So these are objects that are just like free-floating, planet-sized objects. They're about the size of Jupiter. They tend to have masses that are a little bit higher than Jupiter, something like 3 to 25 times the mass of Jupiter. We think most of them formed like stars. They're just like a really rare kind of runt of the litter of star formation where you end up with these small little objects just floating by themselves in space. And they have temperatures from about 250 to 450 Kelvin. So they're pretty cool objects, right? 250 Kelvin is colder than the Earth is. 450 Kelvin is a little bit, just a little bit hotter than that, a couple hundred degrees hotter. Okay, so this is the way that we found these objects. And so we looked at the sky to find these objects. Pre-JWST, we looked at the sky, we looked at things that are really bright at 4.5 microns and then basically completely invisible at 3.6 microns. They're invisible because once you get really cold, you have strong methane absorption. And so the methane absorbs all the light at 3.6 microns. So you're looking for objects that are invisible at 3.6, bright at 4.5. We can plot that up on a diagram like this. So this shows you the brightness at 4.5 microns versus that color, 3 microns minus 4 microns-ish in color. And so as you go down on this plot, you get fainter. And as you go to the right on this plot, you get redder and redder to colder and colder objects. So I'm going to show you some of our early observations of these two objects in here. So these are free-floating planet mass, or just a little bit more massive objects that we got really beautiful, spoiler, really beautiful JWST spectra of. But you haven't earned your JWST spectra yet. You have to look at what we tried to do from the ground before we had JWST. So this is our before photo. We'll do like a before and after kind of glam shot. So this is our before photo from the ground. This is taken from an 8-meter telescope, big telescope, one of our best from the ground. Taken where this object is bright, right, from about 4.5 to 5 microns, but it's very hard to see through the Earth's atmosphere at these wavelengths. The sky is bright, there's lots of absorption, very challenging observation. But we looked at this and we were like, we think we see some features in here. We think there's water out in these wavelengths. We think this is telling us that there's some carbon monoxide in there. Now we'll get our JWST. So that's what we had until JWST. And then this is what we have once we have JWST. So now we have this exquisite spectrum. We can see all kinds of things in here. So we're excited about this for lots of different reasons. There's water here. This whole feature is carbon monoxide, and we get like all of the details. Everything in here is features, not noise. There's a little bit of CO2 in here. We didn't necessarily expect to see that, but it's cool. But I'm going to tell you one thing about this, which is down in this part where the object is otherwise really, really faint, right? It's a really kind of dark part of the spectrum. It's where methane is absorbing really, really strongly. And we're going to zoom into it. There we go. We zoom into this feature right here, blown up here. And we see that one of our objects with the catchy name 2220 is just kind of straight across here. But the other object, it actually has this bump here. This bump is methane that instead of absorbing in our atmosphere is actually in emission. So it's glowing at this wavelength instead. We know that this happens in places in the solar system because we can heat up the top of our planetary atmosphere with various ways of heating it up, but one of those ways is actually aurorae. So this is like the northern lights, right? Where we're depositing energy into the atmosphere. It can heat up that upper layer of atmosphere and make it glow at various wavelengths. And so this happens on Earth, it happens on Jupiter, like I'm showing in here. And so we don't have a smoking gun that this is exactly what's happening, because all we can tell is that something is heating up the top of the atmosphere. But this is an object that's just by itself in space. And so other mechanisms for heating up the atmosphere from sunlight, right, are not there because there's no star here. This is just this free-floating planet. And so we're really excited about this. We're asking for more time with JWST to follow it up and really figure this out. But we think that this might be one of the first times we've been able to see aurorae outside of our own solar system. Okay, I'm going to tell you about one more of our really cool white dwarfs. And this is this object down here. So this is an object that we call WISE 0855. Again, a catchy name. This is the coldest one. This is our coldest object we've ever been able to observe pre-JWST outside of the solar system. And so we had done some simulations. This is our simulation ahead of time that said, okay, we think that we'll be able to see deuterium, heavy hydrogen, right? For the very first time in a planet outside the solar system, we think we'll be able to do this. We made the prediction, got the telescope time, and amazingly, it worked. So we can kind of zoom into the wavelengths where we can see that deuterium, and we indeed see the deuterium. So we see it in a deuterated methane feature. So this is like methane, right? CH4, but instead of one of those H's, we swap in the heavy hydrogen. We swap in the deuterium, and we can see it. So this was actually first seen in Jupiter from McDonald Observatory way back in the 1970s. And now we can do it outside the solar system for the very first time. So we're really excited about this. So if we plot it up on this plot that shows how much deuterium there is relative to hydrogen versus the mass of the object we're looking at, we can see that in our own solar system, we have a variety of different deuterium to hydrogen ratios. This is like a classic tracer of planet formation in our own solar system, because the more ice that gets accreted onto your giant planet, the higher your deuterium to hydrogen ratio is. It's also for small planets, this tracer of how their atmospheres evolve over time. So I won't tell you too much more about this now, other than we're really excited to be able to put our first extrasolar object onto this plot, and we're hoping to be able to put a bunch more points on this in the coming couple of years. Okay. And so these objects that I showed you, we can get this really nice data in part because they don't have a host star that's like right there next to them. But JWST is actually allowing us to detect some what I'll call kind of true Jupiter analogs. These are actual like Jupiter's orbiting stars on kind of Jupiter-like-ish orbits. And JWST wasn't designed for this. And so when you figure out the math of what we can actually do, it turns out that we can only do this for the nearest stars, which is actually kind of fun because it means that we can just do it for like named stars with like better names than like HD 209458b. And so the planet that I'm going to show you orbits a star that has had like a science fiction planet around it forever. And so this is Epsilon Indi. I'm showing this is like the Wikipedia page on stars and planetary systems in fiction. And you can see that Epsilon Indi hosted a star back in like Star Trek original series, right? You got a planet around Epsilon Indi. For more like younger people, when I'm talking to like high schoolers, right? They maybe play Halo. In the Halo universe, Epsilon Indi also plays a role. So there's something for everybody, no matter what generation of sci-fi you grew up in. Okay, now I'll show you the actual planet. So now we can actually observe Epsilon Indi. So this is at 10 microns on the left and 15 microns on the right. We had predicted that there would be a planet around Epsilon Indi because we could actually look at the star and see the star moving just a little bit. But we didn't know exactly how big the planet would be and where it would be. We could just tell that there was something there that we couldn't detect in another way. But it's just like whopping bright detection at both 10 and 15 microns. And so from this, we can start to constrain what this planet is like. We can see that it's just under 300 kelvins. This is one of the coolest objects, coldest objects we've ever been able to see. And it has a mass it's a little bit massive, right? It's something like 10 to 12 Jupiter masses. And this is the first true Jupiter analog that we've been able to directly image in this way around a kind of nearby kind of solar neighborhood star. So that's been really fun. We're again applying for more time. Now that we know it's there and it's so bright, we think we can actually get spectra of this. And so we're writing up the case right now to the allocation committee to try and give us more time to look at this again, but with spectra instead of just photometry. Okay, I can't come and talk to Texas astronomers without telling you about something that we've done from McDonald Observatory and the Hobby-Eberly telescope out there. And so I decided this is my like interlude in the middle of the talk where we come back to Texas and I tell you something cool that we can actually do from the ground rather than just looking from space, even though space is fun. So I'm going to tell you a little story about what happens to planets when they like dare to get too close to their stars. And so we've known this for a while, that sometimes planets get too close to their host stars. When that happens, they can start kind of evaporating away. They start losing some of these are all gas giants, so they start losing some of the hydrogen and helium that makes up their atmospheres. And so one of the ways that people have started to look at this just in the last few years is with this infrared feature. So this was actually first seen with the Hubble Space Telescope. And so what you're looking at here, we're back to transmission spectra where the planet crosses in front of the star. And so when Jessica Spake, who observed this, was looking at this data, she was a grad student at the time. She's like, there's something wrong with my data. I always get this point that's like high up here, and I don't understand why. Like, I don't think there's anything wrong in what I'm doing. I've checked it. I've run the equations for the data reduction a bunch of times, and I always get this spike here. But then she showed it to somebody else. They said, hey, you know what? I think I know what that is. That is a helium feature that we actually see in stars, but we might be seeing this in this planet. And indeed it is. So the Hubble Space Telescope is actually not the best facility for doing this. You want to do this from the ground where you can look at this line with a higher resolution spectrograph so you get more points in your spectrum. So let's do that and zoom in to this region. So this was taken with a 3.5 meter telescope in the Canary Islands on the Carmenes spectrograph. We've now zoomed into this kind of 830 angstroms to this helium feature. And in fact, you can see that it's not just one point up here, right? We have this whole feature. It's actually a triplet. There's 3 different kind of features all added together in here. And this is from helium, and it's from helium. There's so much excess absorption. This goes up so much on this plot, right, where you have this excess, that we can tell that this helium is not bound to the planet, right? It's like beyond the bound region of the planet, floating away from the planet. And so this is like an exosphere kind of region that's showing us that this planet is actually evaporating right now. So people started doing these observations right around the time that I moved to Austin and started looking around, you know, to the facilities that we had here, starting off as an assistant professor, right? And I'm like, oh, should use our facilities that we have here, because that would make them really want to, like, you know, tenure me, keep me on here as an associate professor. And so anyway, so we saw that they had this little 3.5 meter telescope, but everything's bigger in Texas, right? So we have our Hobby-Eberly telescope. It's a 10 meter class telescope out in West Texas. Maybe you've been out there before to McDonald. This is in the same area. And it had a new, at the time, spectrograph on it, which was a near infrared spectrograph called the Habitable Zone Planet Finder Spectrograph, HPF. And this had been installed to do measurements to discover planets, but we saw right away that we could use this in exactly the same way that this team in Spain had to observe helium. And so we started this program. So we started this program to observe a whole bunch of these transiting planets with the Hobby-Eberly telescope, looking for these escaping atmospheres. So the way this works, right, a planet transits for about 1 hour every 3 days or so for a typical hot Jupiter. So we're looking to observe at that time when the planet is transiting. But if you, one idiosyncrasy of the HET that is not true for almost any other telescope in the world is that it's a fixed elevation telescope. So it just points like side to side, right? It doesn't actually point up and down. And so if you think about what that means for what objects you can see, right? You can look at objects in most parts of the sky, but you can only see them at the right time of night. And so we get either 1 or 2 tracks per night, depending on the time of year and the location in the sky for any given object. And so we have our HET tracks, we call them tracks when our object is up. And so we can also like look up, okay, when are all of our tracks for this planet? And we look up when do we align, when the HET can look at our target, and when the transit is actually happening, and we choose to observe there. And then we need some out of transit kind of comparison data as well to see, okay, what does the star look like when the planet's not in front of it? That's like our reference information. And so then we pick a bunch of out of transit tracks so we can see what's happening over time with our planet. So we observe the full transit track, then we observe actually the night before, 2 nights before, night after, 2 nights after. This is like a very goofy and weird way to plan a transiting planet program, but it's what we did because of our idiosyncratic telescope out there. But we tested this on a target that we knew had helium, like this helium exosphere around it, and it worked. So this is the kind of data we get. This is like zoomed right into that feature. We have our helium feature here on the right side of the plot. This is a silicon line, just so you can see a different line that's not changing. And so the silicon line is unchanged, but our helium line, you can see this black line here, this is our during transit track, and you see it's deeper. So that's the feature we're looking for. On the plots that come, I'm going to show basically how deep is this helium line and how deep is it over the course of the planet's orbit. So we were very excited because it worked with this kind of idiosyncratic design. And it basically matched the prior observations that showed that there was this helium around the planet that kind of had this tail coming off the end. Then we like launched our program, right? We looked at about 20 different planets. We looked, and I'm going to tell you about 2 of them because these are the 2 that had like exciting, cool results. So one of those is HAP-P67, and the other is HAP-P32b. These are quite similar to each other. So these are both very puffy planets. They're pretty low mass, right around Saturn's mass, but they're puffed up to the size of like twice the size of Jupiter. So we think they're getting puffed up by their host stars, kind of putting energy into them from being so close to their stars. They're both around F stars, which might not mean anything to you, but it means it's around a star a little bit hotter than our own sun. And they both have very similar temperatures to each other, right? Just under 2000 Kelvin. If you plot these up on a plot of the planet mass versus the planet radius, so like the things at the top of this plot, right, are very low density. They have really high radii for their masses. And so these planets are both some of our lowest density planets, our puffiest planets that we observe. Okay, so I'll show you HAP-P32b first. So this is what the helium, the depth of that helium line looks like as a function of time. And this is for the planet's whole orbit. So we start here, see no change, no change, no change. But then we start to see this go up. And in fact, this goes up well before the planet itself, right? Like the normal planet part starts going in front of the star, which is this like dark gray region in the center is the actual transit. And so it starts going up way before. That means that we actually have this like geometrically extended tail that's going ahead of our planet in its orbit. And so it peaks up here during the planet's transit. We expect that. And then it starts coming down here and is still high after transit. And so what we see here is that HAP-P32 has these tails that once you do the math, you figure out extend about 50 times the radius of the planet out from kind of both sides, but more before the planet's transit and a little bit less after. That was really cool. And then we looked at HAP-P67's data and realized that it basically looks the same, but a little bit different. So this is again plotting that depth of that helium line. as a function of the planet's orbit. You see it goes up, 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 peaks here, but then comes straight down after the planet's transit. So this is cool. This means that we actually have a tail that's just before the planet and doesn't come after the planet. So we think what's happening is that you're just losing helium on the day side of this planet, and then it gets kind of sheared out in the orbit in front, and then kind of cuts off right afterwards. Here's a pretty picture. This is a pretty picture that actually does physics. So this is from a 3D simulation of what could be happening in the HAP-P32 system, where you see indeed, if you kind of launch material off of this planet, then it can form into these tails that kind of go both ahead of and behind the planet in its transit. And so we think that's what we see, and these extend truly like dozens of planet radii away from the planet itself. Some of our collaborators actually looked at this to see, is this what we expect to happen? And so this is going to play as a movie. Each of the dark kind of points, the bigger points on here, this is a model of a planet, and the planet will evolve over time. So it starts at 0.001 gigayears, and then we'll evolve the system to see what happens to our planets. There's three effects that are happening here. The planets are naturally kind of cooling down over time. That's what planets do. The star is also injecting energy into the planets to kind of puff them up. So that's our kind of two competing effects, the natural shrinking versus puffing up from the star. And then the star is also causing the atmosphere to evaporate away, right? It's kind of blowing the atmosphere away at the same time. And so we see these competing effects, and we'll see how it affects planets that have different masses and radii differently. Okay, so here we go. Here's the video. So you can see that as planets kind of cross over this suggestively drawn line here, they start, the evaporation of the planet starts to win. They're getting puffed up to low densities, and they get really susceptible. I'll play it one more time for you. They get really susceptible to losing their atmospheres. And so what we think that we're seeing here is planets that have kind of just crossed over into this region. And so we're seeing them at this unusual phase of their life. They're kind of end stage giant planets. So we think we're catching these planets in the end phase of their lives as giant planets. We don't actually really know exactly what happens next to them after this. It's possible that their like cores still end up surviving there. And maybe some of the planets that we see at later stages of their lives are actually stripped cores of old giant planets that got destroyed. So we're trying to figure out if that's true about some planets too. Okay. In the kind of last section of my talk, I want to talk about planets that are a little bit closer to home. So we're going back to JWST and what we can do with JWST. And now we're thinking about planets that are more similar to our own planet Earth here, more similar to Venus, right? So this is Venus, or more similar to Mars. So we have this whole story for our own planets in our own solar system and how they got their atmospheres, right? So we think that they all formed with kind of the same, roughly the same budget of volatile material. So about the same amount of water, about the same amount of CO2, kind of all locked in their interiors when they first formed, and then volcanically outgassed over time, right? That Earth is constantly having more CO2 put into its atmosphere from volcanism. We have this whole story about how Venus and Earth, right, start really similar but end up really different. So on Earth, we have the oceans. The oceans are super important for the evolution of the atmosphere on Earth. The oceans allow us to kind of lock carbon dioxide in the oceans, right? So a lot of our carbon dioxide is in our oceans. And also you start to form carbonate rocks. And so a lot of the CO2 on Earth is actually in the deep interior of the Earth as these rocks, and then can be kind of outgassed over time. Venus is too hot for oceans, right? So Venus doesn't have oceans. If it had oceans early on, they evaporated into kind of the upper atmosphere of Venus. Once water gets way up into the upper atmosphere, it actually gets really easy to lose. And so you start to lose water from the top of Venus's atmosphere. You break up that H2O, right, into the oxygen and hydrogen. Then the hydrogen is so light, you just lose it. Same kind of atmospheric escape process as our hot Jupiters, but now on Venus. And so Venus loses its water. It doesn't have any way to put its CO2 into carbonate rocks because it doesn't have water on the surface. And so all of the CO2 just builds up in Venus's atmosphere. Now Venus has like 100 bars of CO2 in its atmosphere, and it has a surface that's 1,000 Kelvin, right? It is not a good place to hang out. It's not an easy place to send spacecraft because of that. They all, get corroded in the sulfuric acid clouds in Venus's atmosphere, and like it's hard to get to the surface. Okay, so that's Venus, totally different path. And then Mars as well. Mars is small, right? Mars is a lot smaller than the Earth. We think it was also susceptible to just losing almost all of its atmosphere. So it now just has a few millibars of CO2 left in Mars because its surface gravity just wasn't able to hold on to its atmosphere. We also have one other terrestrial planet in the inner solar system, right? Which is Mercury. Mercury gets so much radiation from the sun and is small and light and low surface gravity to hold on to its atmosphere. Mercury doesn't really have any atmosphere at all, right? And so when we look at terrestrial exoplanets, we want to know which of these 4 terrestrial planets from our own solar system are those exoplanets that we're finding, that we're really hoping we find atmospheres of life and all of these things on these atmospheres. Okay, so we're going to look at that and see what are these terrestrial planets actually like. So we're back to this picture again. This is the picture we started with talking about atmospheres, right? Where we have 2 geometries, one where we're looking at the planet as it transits in front of the star, and then thermal emission. So with an eclipse, when the planet goes behind the star. I'm going to put up an equation, not to like scare you away, just so that I can explain why this is hard for the terrestrial planets. So the size of the signal that we see scales with this equation here, where this RP is the radius of the planet, and this H is the scale height of the atmosphere, which is like how puffy is the atmosphere. Our scale height on Earth is about 8 kilometers. And the signal during the eclipse scales with this equation. So again, the radius of the planet, the radius of the star, this is now the temperature of the planet and the temperature of the star. And so our fundamental problem here is this, that the signal scales with the size of our planet. These planets are small, and so the signal is small. And in fact, the signal is so small that if you put this little planet around a star that's like the sun, right, the size of the sun, it is underneath our, what we call our noise floor, right, the smallest signal we could possibly see because of systematic kind of errors. So that's our floor, that we can't look at signals that are smaller than that. It's measured in kind of parts per million. So we can see very small signals, but not as small as an Earth-sized planet around a sun-like star. But we have one thing we can change in this equation, and that is the size of the star. And so our trick here is that we observe planets, small planets, only around the very smallest stars. That makes this our star very small, right? And that makes the signal, the intrinsic signal of our planet, larger. So let's look at a picture as well. So this is going to be to scale. This is the sun. This is Jupiter. This gives you something like a 1% transit depth when the planet crosses in front of the star. You can measure that, like I did this as an undergrad, right, with just a telescope in Massachusetts, a 14-inch telescope in Massachusetts. I could measure Jupiter's crossing in front of sun-like stars. 1% photometry is straightforward. For the very smallest stars, right? So this is a star that's like the very smallest you can possibly be and still be a star. If you put an Earth-sized planet in front of it, you actually also get about a 1% transit depth. And so what we're hoping is that we'll be able to do the kinds of detailed measurements that we do for our kind of hot Jupiter-sized planets, right, in front of sun-like stars, we'll be able to do for these little terrestrial planets around the very smallest stars. And what we figured out ahead of the launch of JWST is that really, if we want to look at terrestrial planets that are similar in temperature to Mercury, Venus, and Earth in our own solar system, the only ones that we'll be able to actually observe the atmospheres of are around really small stars. Really small, we call them M dwarfs, right? When they're these really small stars. But there's a problem with that, which is that these small stars, these little red dwarfs, are very different from sun-like stars. So these are stars that are flaring a lot. They're kind of fully convective stars. They flare a lot. They have really high X-ray flux. The sun, right, pretty quickly gets onto what we call the main sequence, where it's kind of steady in the amount of light that's coming out. These little M dwarfs take literally 1 billion years to get onto the main sequence and kind of steady out their light. And so what you're seeing is that planets are getting just a ton of radiation, a ton of high energy radiation, a really strong stellar wind, right? It's like the worst solar storm that we've ever experienced, right? But just like all the time on these little planets. And so what we're worried about is that these small planets around these small stars, the only ones we can see, right, with JWST, are actually all going to be just like have their atmospheres annihilated by these really active red dwarf stars. Nonetheless, we are observing them so that we can figure this out, right? Do they actually maintain their atmospheres? Are they kind of continuing to outgas for billions of years as well, and thus able to have atmospheres? And so this is kind of the landscape of what we're doing right now. So this is showing the size of the planet compared to the size of the Earth on the x-axis, and then the temperature of the planet from heating by its host star. So if you were to plot Earth on this, right, Earth's equilibrium temperature, something like 250 kelvin, so it'd be here, then 1 Earth radius. So it'd be right in here. So we're looking at planets. The different colors are telling you kind of which geometry we chose to look at them: transit, transmission geometry, or the emission when the planet goes behind, or if we're looking at the whole orbit. So for some of these, we can actually do what we call a phase curve and look not just at transit or just at eclipse, but at the whole planet's orbit, right? Like imagine looking at all the phases of the moon. We can't talk about all 25 of these. In fact, all 25 are not yet even published because JWST is, still taking some of these measurements. But today we're going to talk about these 5. So a couple transit, a couple, a couple eclipse measurements, and then one at the end. So let's start in transmission, planet in front of the host star. So I'm going to show you a bunch of plots that look like the one I'm about to show you. It's a little bit messy. What we're going to be looking at is these black data points here is our actual data. So this is infrared from 3 to about 5 microns. This program was designed so that if we had kind of a Venus-like atmosphere with lots of CO2, we might be able to detect that CO2. So each of the lines on here is just a different model atmosphere to compare to with a different composition. So like this purple line in here, that's just water, 100% water making up the atmosphere, like steam atmosphere. The blue one is Earth-like. And so what you can see here is that for this planet, so this planet is almost exactly the same radius as the Earth. It's a little bit hotter, right? This planet is almost 600 Kelvin. And it's around one of these nice small little stars, a star that's about the third the radius of the sun, about 3,300 Kelvin. What we see here when we look at it is that these points, these black points along here, are best fit with something totally flat, right? Just a flat line ends up being the best fit here. What that is consistent with is having just our kind of Mercury case where we have our bare rock and no atmosphere surviving around it. So we think that this is consistent with kind of no evidence for an atmosphere on this planet. Okay, next planet up, GJ 1132b. Very similar sized planet, right around the size of the Earth. Very similar kind of M dwarf, little red dwarf host star. They did their first visit for this planet and could see this kind of bump up to here. This is at exactly the same wavelength as water absorbs. And so they looked at that and said, hey, that looks really cool. That looks like there might actually be water in this terrestrial exoplanet atmosphere. That would be amazing. But the people who designed this program, right, knew that there are also star spots in these cool stars. And in fact, the star spots in M dwarfs, because their overall atmospheres are so cool, right, 3000 Kelvin, when you have those even cooler star spots, those are actually cool enough to have water vapor in the star spots. And so when that happens, they can actually introduce kind of fake water vapor signals into your transmission spectrum. And so they know that star spots vary, and so they plan an observation for a few months later when the star spots may have kind of rotated out of view or otherwise changed. And they see that that visit is totally consistent with the flat line. And so for this planet, I think we learned a few lessons, right? We need to observe multiple times with these small planets. We need to really understand the stars really well, including spots on those stars. And so far, from looking at the transmission spectra of these and also some other observations, we have no transiting planet evidence of atmospheres yet, but we're still looking at more of them, maybe ones that are slightly cooler, right? This is still 500 Kelvin. Maybe as we get cooler, they'll be kind of less irradiated by their stars. We'll be able to hold on to more atmospheres. Okay, now we're gonna do thermal emission. So this is an eclipse, right, when the planet goes behind. So I'm gonna introduce you to astronomers' favorite new set of planets. This is the TRAPPIST planets. The TRAPPIST planetary system, the TRAPPIST star is actually just barely a star. So this is about 1/10 the mass of the sun. The temperature is something like 2600 Kelvin. So this is a very, very cool star. It's an M9 spectral type. And it has this whole set of planets around it. So it has 7 transiting planets that are all orbiting close to this little tiny star, just barely hanging on to the main sequence and burning hydrogen into helium. Okay, so the plan here is to observe the inner 2 planets. So TRAPPIST-1b has a temperature that's kind of between Mercury and Venus, heating it up from its host star because it's in this close orbit. TRAPPIST-1c is our kind of planet that's closest to Venus in how much light it's getting from its host star. And so through these 2 different programs that I'll show you the results from, the idea is to observe 4 eclipses of TRAPPIST-1c and 5 eclipses of TRAPPIST-1b. So we have to observe lots of times and kind of build up that signal. And the idea is to distinguish between a bare rock and a kind of Venus-like CO2 atmosphere. And so this is what we simulated, is if we had a bare rock, we would have this strong signal. So if we have a bare rock, there's 2 things that give you a strong signal. One is that you have this bare rock that just heats up a lot. So you have like a dark bare rock, you're kind of hitting it on one side because these are also tidally locked to their host stars. You're heating it just on one side, can heat up a ton. If instead you have a Venus-like atmosphere, 2 things happen. One, that atmosphere actually takes some of that heat that's hitting your planet and circulates it around to the night side. So your day side will actually look cooler on a planet with an atmosphere than a planet without an atmosphere. The other thing that happens is we designed these observations to be observed right at 15 microns, and we did that deliberately. So 15 microns is a region where carbon dioxide has this really strong absorption feature. And so if there's no carbon dioxide there, we'll see the planet really brightly. If instead we have some carbon dioxide there, we'll also get that absorption, and that'll make our planet look basically invisible. So the hope here is that our planet is almost invisible to us. And that would tell us that there is this kind of thick atmosphere on the planet. Okay, so here's what our data looks like. We'll start with B and then we'll go to C. TRAPPIST-1b looks like this. So the black points here are the data points. The red is our best fit eclipse model. So we get this very straightforward kind of deep detection here. It doesn't look that deep on this plot, but it's statistically deep. That gives us this point here, which is totally consistent with these lines that are the lines for if you just had a bare, heated up, dark rock, that's what you'd get. Whereas these lines down here, this is including that carbon dioxide absorption feature. And so the data for the very first planet, TRAPPIST-1b, rules out essentially all atmospheres, certainly any atmospheres that have carbon dioxide in them. Now I'm going to show you TRAPPIST-1c. So this is what our eclipse looks like. So this is not quite as deep as our TRAPPIST-1b eclipse. That's because the planet is cooler. But we see this kind of flat line, and then we see this eclipse in here. So again, we're able to detect this. It tells you right off the bat, this planet is not invisible. We were able to detect it. And in fact, if we plot it here compared to some different models, we see that it plots up here where it could be kind of equivalent to having what's labeled here, this dark black line, ultramafic rock. That's like a really iron rich rock, like a really dark rock on the surface might be an ultramafic rock. And so the data for TRAPPIST-1c is less conclusive in ruling out an atmosphere than the data for TRAPPIST-1b. It does rule out all of our kind of Venus-like atmosphere scenarios, these thick CO2 atmospheres, but there are atmospheres that are still possible to exist on TRAPPIST-1c. So we're also going back to look at other wavelengths to really verify this, this information. Okay, I want to show you one more rocky planet observation. So this is going to be for a planet that we actually knew going into the observation did not have an atmosphere, but we wanted to know what the surface actually looked like because nobody's really been able to do that before, right? So we had this planet that we knew from looking with the Spitzer Space Telescope, which is kind of the predecessor to James Webb, that it didn't have an atmosphere, but we could observe its surface with spectra. So this is our one Spitzer point that we had down here. And then with the MIRI instrument on JWST, we could observe these blue points here. So this is a rocky exoplanet, again, around a small star. This is a little bit hotter. This is about 800 Kelvin. And you can see these features here. So we're still working on the kind of final results for this object, but it looks like it's broadly consistent with kind of a basaltic surface. And we can rule out kind of shinier, right, brighter rocks, something more like a granite. If you can picture like the granites in Yosemite, right? We can rule out rocks like that. This is more like if you go to Hawaii and look at like the dark rocks there, that looks more like this planet, LHS 3844b. Okay, I think that's all of the spectra I have to show you. I wanted to encourage you, if you want to kind of get more involved with UT, I think many of you have actually visited McDonald Observatory, so you know that there's a lot going on out there, including like special viewing events at our historic telescopes and things like that. If you're ever passing through Austin on the Tuesday, we do it one Tuesday a month, we have astronomy on tap at a local brewery. Those are always really fun. We do a few different science talks at those and also like trivia and stuff. So we have a good audience at those usually. And then if you ever want to like learn more or get involved in any of our like outreach programs or education, there's also ways to do that, like the Friends of McDonald Observatory. Okay, and I'll close here and say it's been really fun the last couple of years. We've really entered this new frontier of exoplanet atmosphere observations where we're able to do brand new things that we haven't been able to do. And so we're kind of taking our first steps into that now. And so we're able to get this really nice data of all kinds of exoplanets, including these free-floating planets that I showed you. We're getting towards planets in our own solar system, right? Our cold Jupiter analogs. Also, a bunch of other exotic planets that are nothing like the planets in our own solar system. We're able to do cool stuff from the ground too, and I showed you some of those results from the Hobby Eberly telescope here in West Texas. And we have no smoking gun evidence yet for atmosphere detections for these terrestrial planets, but we're working really hard on it. There's lots more data coming, so stay tuned to see what we find in the coming years. I'm happy to take questions now. Thanks for having me.
Okay, thanks. That very interesting. And I'm going to ask Chris Morissette if you want to come off mute and ask your question.
Yeah, can you hear me, Don?
Yeah, I can hear you fine.
Yeah, okay, great. A great presentation. This is a little bit off topic, but did I understand right? Free floating planets are planets that are not orbiting a star. Is that correct?
Yeah, that's right.
And then how did they get that way? How
Yeah,
did they
so we
get to
think that
be free
some of
floating?
them, yeah, we think that some of them just formed that way. The kind of the very smallest things that you can possibly physically form in the star formation process just sometimes forms things that are like 10 to 20 Jupiter masses. It's just rare, and so we don't have that many of them, but we do have some of them. Um, it is also possible, especially as you get to lower and lower masses, that these actually formed in a disk, right? That you formed like a planet does in like a protoplanetary disk,
Mm-hmm.
just like the planets in our solar system formed, and then had some kind of interaction, right? Like a gravitational interaction, and got slingshotted out. As a general rule, you need an object that is more massive than your slingshotted out object to be able to actually throw it out. Otherwise, you just kind of move its orbit around. So to actually eject it, you need something massive. And so we think that that's possible, but maybe not the most likely way to form 20 Jupiter mass objects. But certainly
Yeah.
for like, there's probably lots of Neptunes and Saturns floating around in space that are just hard to see.
Gotcha. And I thought of just one more question. How do you find these planets if you don't have starlight to detect them?
Yeah, so we observed the whole sky at infrared wavelengths and then observed it again and again and again and watched for objects that are actually moving because these objects are close to us, relatively close to us,
Okay.
because they're faint, right? So we can only see them when they're close to us. And so we find them by looking for their colors, that they have different infrared colors than other objects, and the fact that they're usually moving across the sky. These are actually the same surveys that find like near Earth asteroids, but we can use them to find these cold objects as well.
Gotcha. Thank you very much. Appreciate it.
Yeah, you're welcome.
Okay, Joyce, do you want to come off mute and ask your question about the aurora?
Well, yeah, I think yeah, I think there were a couple of us trying to figure out what the energy source was that was causing these aurorae to happen.
Yes, a very good question. Our referee asked us the same question when we were trying to publish this paper. So the picture here, right? So like in the solar system, as many of you know, it's the solar wind that's giving you the ions that are causing the aurorae. That's true for Earth, certainly. In Jupiter, we actually have a combination of things going on. So we have the solar wind that's doing much of it, but we also, in Jupiter, have the Io plasma torus. So Io is volcanic, right? One of Jupiter's moons is volcanic, highly heated by its interactions with Jupiter and kind of the other moons. And so it's got plasma coming off of the surface of Io that is then deposited onto Jupiter and also deposits energy as those ions kind of go onto Jupiter. And so our picture for what could be happening here, but we definitely don't have strong evidence that this is definitely happening, is that there could be like a moon system here, and we'd be seeing something similar to that. But we need more evidence to actually say that that's definitely happening.
so then related, is the methane more sensitive to picking some of that up than other gases would be?
Yeah, so I think it's because the methane is such a strong absorber in this atmosphere, means that methane is causing us to be kind of seeing really low pressures. And I think we can only really heat up the low pressure parts of the atmosphere. So if we've looked at this, and there's some longer wavelengths where other gases might also be coming from similarly low pressures. And so one of our theories is that we should also see those kind of flipped into these emission. And so we want those, I think there's ammonia out there that might also flip into emission. And so we want to see that and test that and see if it's just the methane doing something unusual or kind of all of the gases that are these kind of probing these low pressures.
Okay, Chelsea, did you want to comment? Chelsea's still with us. Well, okay, maybe not.
I'm sorry.
Chelsea.
I was having a hard time with the audio. I'm sorry.
Oh, okay, no problem.
About the teacher workshops. Well, I've been there 3 summers. It's amazing. I go there because I teach science lab from kinder to 8th grade, and they have a lot of astronomy objectives in the Texas curriculum. And being there it's just an experience. This last summer, we were talking about how, as teachers, we need to teach science properly. We need to experience what we do at McDonald Observatory. We have lectures with professional astronomers, and we are taught the research process that you guys do. That's how they teach us, and every, no exceptions, we just go like, wow, I've never saw it this way. It's just a wow week. We can say anything but wow, and then it's very immersive. We do observations. We barely sleep. There's no sleeping. It's just lectures, hands-on, observing. 2 summers ago, we had the experience that we saw this like a fireball, but I think we saw a fireball coming at you in our direction because it was so weird. 15 people with iPhones, not one picture. It's just everybody, So if you're a teacher and you want to have this unique experience, go to the website, look for teachers workshop. This is addictive. I drive 10 hours from Houston to the observatory, and I love it. 10 hours back and forth, worth it. So if there is a teacher here in the audience, or you have a teacher friend, this is like teacher spa moment. I can't recommend it enough. I'm addicted. I go every summer. I guess Judy just dreams about me like, oh, you again. It's the best I ever experienced as a teacher for a workshop. You get 10,000 hours for professional development. So I love them. You can tell. And I'm a friend of McDonald's, so I have my membership. And we stay at the Astronomer Lodge, by the way. Unbelievable. I stay at the Astronomer Lodge, and we get to meet some of you. We understand we should not be distracting you from your matters, and we need to be quiet. But it's so amazing. I love it. I can talk about it a whole night. Just thank you for opening for teachers. Thank you.
That's great. I'm so glad that you've been to those programs. That's awesome.
I wanted to make a real quick comment. I've been kind of paying attention to exoplanet research for probably 15 years, right? And it seemed to me like there was this big shift towards M dwarf stars and observing around M dwarf stars, and I never really understood why. And I appreciate your explaining to us that why that is. It's like you want super Earths around real small M dwarf stars, and now you can get good data. And that just finally clicked. So thank you for that insight.
Yeah, you're welcome.
Dan, you want to come off mute?
Yeah, I'm an engineer, so I am interested in the instrumentation, and I understand that we've had quite a bit of trouble with near-infrared detectors in the past, and I understand that there are still some trouble with near-spec in particular that maybe have an impact on you. So I wonder, how do you handle that? It's a wonderful instrument, but like all instrument, it has its little quirk. How do you know if it is degrading, and how do you handle it when it does? Because the signal-noise ratio is so disfavorable. You know, you have to watch it. Thank you.
Yeah, my understanding, and like I'm not connected to a space telescope that's dealing with the stuff on a kind of day-to-day basis. We're still learning a lot about the observatory. And so like within the very first couple weeks really of science operations on JWST, we were getting more impacts on the telescope, like micrometeorite impacts than we were expecting. And so we're doing things like deliberately observing in certain configurations that will make the facility just last longer if we're not looking kind of in the direction that we're orbiting, right? We're looking in different directions. The detectors themselves, I think my take is that people are most worried about our one mid-infrared detector. So that's MIRI. It goes from 5 to 28 microns. I know that there's been various technical issues with the moderate resolution spectrograph, MRS mode, on MIRI. And so I think none of us are quite sure exactly how long that detector is going to hold up. It's a different detector technology than the near infrared instruments. I think the near infrared instruments are holding up as expected in space. And so we're expecting those to definitely last a long time. And I think we're learning to deal with the quirks of them as they are flying in space now.
Okay, that's the last of the questions on the chat. Anybody else would like to come off mute and make a comment or ask a question?
Yes,
Don,
I would
this is
like
Bill
to ask about
Spizzirri.
life.
Well,
I'm sorry. Go ahead.
Yeah, Don, this is Bill Spizzirri. I had a power failure during the presentation, so my whole chat disappeared. So my question is, Dr. Morley, in your fantastic presentation, thank you very much. Very early on, you had a screen that showed the techniques that you use to find planets, and one of them was called timing variations. I don't know what that is. I didn't see you describe that unless possibly I missed it.
You didn't miss it. I didn't talk about it. So for timing variations, I think that lumps together two different kinds of timing variations. One of those is pulsar timing. So the very, very first planets that were ever discovered were actually around pulsars, which are like rotating magnetic neutron stars. And so we look at tiny timing and exactly the pulsations that we get from the neutron star, and that tells us there's a planet perturbing the orbit. But it also, I believe, is lumping in transit timing variations where you have a multi-planet system with multiple planets all going around. Those planets hug on each other gravitationally, especially in kind of certain orbital configurations. And so we see changes in exactly when the transits happen, and we can infer that there's kind of unseen planets in the system that are kind of not quite transiting. Maybe they're like just out of the plane. So they're not transiting, but they are gravitationally affecting the other planets. And so we also call that timing variations because it's a transit timing.
Well, you guys are making use of that telescope, doing a very good job. Thank you very much.
Yeah, you're welcome.
Dan, did you have another comment?
Yeah, my question is about the optimism that we humans put into imagining life on other planets. You showed us very clearly the difficulty of the signal-noise ratio is horrible. And then you have red dwarfs that are known for having a tantrum, and you have planets that are typically tidally locked because they are so close. So on one side, you fry. On the other, you freeze. So I wonder if we are not a little bit too optimistic looking at this spectrum and saying, there is oxygen, there is methane, there is CO2, therefore there may be life. What do you think about this interpretation of the data?
Yeah, a very good question, the kind of question that keeps us all up at night. I think, I mean, the reason to look at the planets around M dwarfs now is that we can, right? Our facility instrument that we have now is sensitive to those and is not sensitive to planets around sun-like stars. So even if we think that it's less likely that life is forming on those planets, it is something that we can look at now, and so we want to look at it now. We're also working on technology development to be able to observe planets that are more like our own Earth around a sun-like star. Unfortunately, that's really hard to do. We basically can't do it with transits anymore. We have to actually block out the starlight and observe the planet itself. The planet is something like 10 to the 10 times fainter than the star. And so that is a very, very technically hard problem. And so we're working on it, but that's going to be an instrument that's probably going to launch in the 2040s, which like I look at that and I'm like, oh, I'm going to be, maybe at the very end of my career, when this is actually giving us science data. I do think that, I'm optimistic that we have lots of planets out there. We see life in all kinds of places on Earth and even like surviving in the space environment. So I'm optimistic that if you can actually have atmospheres that survive on these planets and liquid water on these planets, and we should be able to start characterizing that soon, I'm optimistic that life is actually pretty common in our galaxy. We just have to build the technology to find it.
Okay, I think there's also the rare earth hypothesis that says, that's asking a lot, and we really don't have the technical capability yet to know whether it really is a rare earth hypothesis sort of thing or not. So hopefully, and I'm with you. I hope the technology takes us to the point where we can say, yeah. There's definitely something there that says life. So anyway, I just if anybody else has anything else to add, if not, I just want to thank you very much, Dr. Morley. Lots of comments on the chat, Sam, complimenting you on such a great presentation. Thank you so much, and like I said, my offer still holds. If you want to come out to Texas Star Party, we can make it happen.
Great. Thanks for having me.